Hello, folks. Today we'll be doing this magnetic field lab. So here is a little bit of conceptual overview and what we are doing in this lab. So this is magnetic field lab, magnetic field lab. So a magnet always comes in dipole. So we have a magnet here, another magnet. If they are same poles, they repel, and if they are opposite poles, they attract. Just like the like charge property, like opposite charges they attract, same charges they repel. So here they will be attracting. Okay. They also create a magnetic field. For example, if we have a bar magnet and the magnetic field will start originate at the north pole here like this, and it will go like this, will end here at the south pole. That's how we saw the arrow. It's exactly like if you recall when we did electric field, the arrow was shown like this. If we had positive charge here, negative charge here, and that we said electric field is pointed this way from left to right. So the arrow here was showing our electric direction of the electric field. Same thing here. If we have a bar magnet, the magnetic field starts at the north pole and ends at the south pole. Okay. We also have uh, magnetic field. Let's say if we have a wire, okay, in which we have a current passing through. Okay, in this wire, we can actually find this wire will create a magnetic field around this. Okay, and we can actually find the magnetic field by this equation. So magnetic field can be found by mu naught times I divided by 2 pi r, where mu naught is permeability in free space. It's a constant, so mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. Okay. And it's a constant here. And I is the current in the wire, and R is the distance from the wire where we are looking for the magnetic field. For example, if you're looking for the magnetic field here, that distance R is called that distance from the wire, and we'll find the magnetic field here. The magnetic field is also a vector quantity, and the SI unit for magnetic field is Tesla, that to honor the scientist Nikolai Tesla. So 1 Tesla actually is 10 to the 4 Gauss. This is the symbol for Gauss, where Gauss is the CGS unit. Tesla is the SI unit. You can also break down Tesla into smaller units. That will be 1 Newton, 1 Coulomb per meter. Okay. That way we can define Tesla, Tesla in basic units. Okay. Let's say if we have a coil, we can also find the magnetic field of a coil. So it has the equation will be the magnetic field of a coil is uh, mu naught times I, and if it has n turns, there will be n here divided by 2r. And if you recall, this equation is a little bit different than the equation we had on the previous page. On the previous page, we had little r, lowercase r. Now we have uppercase r. That uppercase r is actually this radius of this circle or this loop. Okay, we can find the current here by putting an ammeter, and then basically so what will happen is if we have a loop, it creates a magnetic field to the center of the loop. Okay, and to find the magnetic field, we can use this equation. And in this equation, again, the mu naught is the permeability of free space. I is the current. N is the number of turns. If it is only one turn, N will be 1. R is the radius of this loop or circle. Okay, and that way we can find out the magnetic field created by this loop, which is passing through the center of this loop. Okay. Uh, we can measure the magnetic field at any given location. To measure, we have to use another magnet that's called a compass. So a compass has a red and usually green one here for south. So the red one shows north and the green one shows south. And that's not true all the time. Different textbooks, different uh, depending on where they're using. Almost everywhere the red needle is for North Pole, and for South Pole I have seen like blue needle, green needle, even white needle. Okay, but most of the time you will see for North Pole we'll have this red needle. Okay, so compass has two jobs. The first thing is it detects the magnetic field in a particular at a particular location. For example, you might have seen when if you ever use GPS, that uh, the arrow, the red arrow in the GPS always shows you the north direction, right? So that's one of the jobs of compass. It tells you the direction, or from north you can figure out other cardinal directions like east, west, and south. And the other job is to figure out the shape of magnetic field in the presence of another magnet. For example, if you have a magnetic field because of a coil like this, if you bring a compass here, they will start interacting because both of them are magnet, because compass itself is a magnet, right? So the other job of compass is to figure out how the magnetic field is located in presence of another magnet. Okay. Earth that we live in also has a magnetic field. What happens is Earth, inside the Earth's core there are like molten iron, and since Earth has a motion, okay, uh, like it has two motion. It's revolving around the sun and then it's rotating. It's a spinning, right? So because of this motion, there this molten lava actually is creating a magnetic field through the center of Earth. The axis of that field is to the center of that Earth. Okay. So it turns out if you have Earth, planet Earth, the magnetic field points like this. The magnetic field in the north is pointed downward and south is pointed up. That's not what we know so far, right? Remember, on a GPS, the needle always shows up. So what that means is the geographic pole, geographic north, geographic north is towards the north side here that we are used to. It's also called our true north, and the magnetic north of Earth is this one. Okay. And the reason behind this probably is like if you bring a like compass again here, this compass again has a needle, north and south, north and south. So this north will align, this magnet in the compass will now align with Earth's magnetic field and align like this. So it shows you the north is aligned here. Okay. So for our convenience to understand the direction, we say geographic north is up and geographic south is down. But that geographic north is actually the magnetic south of Earth's magnetic field. Okay. So something to keep in mind. Uh, and again, that magnetic field is created by the molten iron in Earth's core, and Earth is moving, it has a motion, that motion is creating the magnetic field. And remember, Earth is a ferromagnetic material. Like those who are very good magnets or show magnetic property, they are called ferromagnetic. Those who show magnetic property under certain conditions, they are called paramagnetic. And there are materials that don't show any magnetic property at all. For example, wood. No matter what you do, it will never show its magnetic property. It's not a magnet. It does not have a magnetic property. Okay, this is called diamagnetic material. Okay, uh, if you had to do this lab in real lab environment, what you could have done is you can actually find out Earth's magnetic field in Thibodeau. What you do is you have a coil of N turns and you supply the current through this. Okay, and that's connected to the ammeter here. That's connected to a battery or power supply. Okay, so you know this current here. You can find the magnetic field here of this coil by this equation. N turns mu naught times I, that you can measure with the ammeter, divided by 2R. That's the radius of this coil, R here. Okay, that's a loop or coil, you can say, the loop or coil. And since now this loop is creating a magnetic field, there is already a magnetic field because of Earth, right? So two magnets, as I said, like magnetic field is a vector quantity, they will start interacting. So there will be resultant. Okay, this is how it will look like. So if you have the magnetic field because of Earth and magnetic field because of coil, there will be a resultant of these two vectors that will point like this. And you can measure the angle, this deflection theta here. So in the measurement of Earth's magnetic field in theta, what you do, you put a compass here. Okay. And as soon as you turn on the switch, there is a current in the loop, and that will create a magnetic field of this loop. So the magnetic field because of the loop will interact the magnetic field because of Earth, and the compass needle will be deflected. And that deflection here, you can measure as theta. Okay. So then you have to modify the equation. There is tangent theta here, and you can basically find out magnetic field of Earth. Okay. What we are doing with PhET simulation, so this is what you are doing. You will open an internet browser. On that browser, you will search PhET simulation. So PhET, and in that PhET simulation, you click on this one. Then you search for physics right here. In the physics, you will go for electricity and magnets, and then you're looking for magnets and compass. So magnets and compass. This one, you cannot run this on the browser itself. Some of the PhET simulations you can run in browser itself. For this one, you'll have to download it. So download it on your desktop or in your computer somewhere. Keep track of the folder where you're downloading. Then from that folder, open this simulation, which is a Java file. If your computer's Java is not updated, or there is no Java at all, it will give you an error. So make sure your computer or laptop or PC, wherever you're downloading, have the Java file updated. Okay. I have this already downloaded, so I will open that. When you open this, this is how it will look like. Okay. So when you open this, um, you just have to make the strength 100% and uncheck all these boxes and move this magnet a little bit. Okay. And then the handout that I have shared with you, in that handout, follow the activity. Okay, so first thing you're doing is you're looking for the field, how the magnetic field of a bar magnet looks like. Okay. So you're looking something like this. Uh, so in this field, you're looking, so this is how the magnetic field of bar magnet looks like, right? You can flip the polarity. So you flip the polarity, again, see here. Then you can bring in a compass and see how the compass needle interacts with this bar magnet. Okay, and with that, you can also now put how the magnetic field of planet Earth looks like. So magnetic field of planet Earth looks like this. But remember, we had flipped the polarity, so make sure you fix that one. So you fix the polarity, and now this is how the magnetic field of Earth looks like. So true, the magnetic field is like North pole is downward, South pole is upward. That's the magnetic north and magnetic south. But remember, geographic north and geographic south, they're opposite. Okay, and do all the activities, then take the screenshots, paste that in MS Word file. Then there are a couple of answers, answer those questions, and then turn in these files. If you convert that in PDF, that will be easier for us to open. Uh, and that's how you can share your work with us. And that will be the work for today. Okay. And if you have any question, ask your instructor, and or you ask me, and we'll be able to answer. And that is what we are doing in the lab today for this PhET simulation for magnetic field. Okay. All right.